Welcome to the first grade 12 project, the 3.1 CharlieClock. In this video, I will clearly explain the engineering concepts behind my CharliePlex LED clock project, focusing on theory, design, and implementation. When a microcontroller's pin is set as an output, it can be driven high, connected to power, or low when connected to the ground. This actively forces the voltage level on that pin. However, when a pin is set as an input, it enters high impedance state. This state, the pin is essentially disconnected from the circuit and doesn't drive any voltage or current. It's as if the pin is floating or not connected to the circuit. This allows for external signals to be measured without interference from the microcontroller. This high impedance state is an essential technique in CharliePlexing because it allows multiple LEDs to share pins without unwanted current paths, effectively disconnecting unused pins during each LED activation, preventing more than one LED coming on per cycle. The amount of LEDs that can be controlled by X amount of pins is determined using this equation. This equation is a permutations equation. We use permutation because the order matters in this case, as if pin 1 is high and pin 2 is low, then when they swap their highs and lows, it will be a different LED. This creates another way to use the microcontroller pins more efficiently to achieve more outputs. On my PCB, there are several crystals to be seen, but one of the most important ones is labeled X1 and is right here. This is a 32.768 kilohertz crystal. The 32.768 kilohertz crystal is a special low-frequency crystal that's used in the STM32's real-time clock. This number specifically is used as it is 2 to the 15th hertz, which is easily divided down to 1 second or 1 hertz by binary counters. Due to its low power consumption and integration with the STM32, it's a perfect candidate to keep accurate time for the CharlieClock. This is the printed circuit board, or PCB, designed to physically connect and support all components of the CharlieClock project. A main goal is to pack all of the control components to control 132 LEDs into a compact, reliable layout. At the heart of the board is the STM32 microcontroller, positioned centrally to minimize track lengths to the LED array and peripheral parts. Shorter traces can reduce signal delay and noise, which is critical for accurate multiplexing of LEDs. Near the microcontroller, you'll see a voltage regulator section. The diode's AP2 12K 3.3 volt regulator supplies stable power to the MCU and other components, ensuring consistent operation. The next important part is a 25 megahertz crystal seen right here. This crystal is what I forgot in my version 1 PCB and allows for accurate timing and communication through USB to other components such as my computer. The next crucial part are the decoupling capacitors surrounding the STM32. These capacitors are connected to the 3.3 volt and ground of the capacitor and smooth out and remove any noise or disturbances in the voltage, keeping all measurements and timing in the controller. If you look closely, each capacitor is placed near the corner of each corner of the microcontroller. This is because there is a pair of ground and VCC pins on each corner, so putting the capacitors there minimizes track length and increases the capacitor's ability. The next important part of the PCB is the USB-C, and is the communication bridge between computer and STM32. And even though it looks simple, the USB-C port actually has 16 pins coming out of it. All 16 of these pins connect to the STM32 to ensure data transfer and power, and there are copies of several pins to ensure that even if some break, it will still work. The last important part of the PCB circuit and the final project is powering it. This is done with 2 AA batteries, which each have 1.5 volts. So if the negative of one connects to the positive of the other, and the positive connected to the board, and the negative of the other battery connected to the board as the positive negative, the series connection will produce 3 to 3.3 volts from the 2 AA batteries. And pulling from the STM32 CEU6 datasheet, we can clearly see that the module can run from 1.7 to 3.6 volts. So this series battery connection is perfect for our case. The last important part of the circuit is the user interface. See these 5 buttons here. The first 2, right here, boot and reset. These 2 buttons are used to code the microcontroller. So I press boot and then power cycle or reset. put it in DFU mode. It's now available on the USB-C port to code. I press reset again to start it up again. The three buttons here, set, hour, and minute. These allow the user to change the time whenever they want. So I say I wanted 3:24, I press set, and then hour 3, and then press and hold minute to get it to 25, 26, and then start it up, and the clock will keep time from there. Underneath the board, we have the two AA batteries in series to power the board with 3 volts. You can swap these out at any time if the battery dies. These yellow wires right here are used to code or to power the CharlieClock. So the wires come through here, down through this hole right here, inside the case, and up into the PCB to limit any visible wires to the user.